there is a counterpart to the sampling that we've been doing in the time domain. It's actually sampling of the Fourier transform, and this is called spectral sampling. So I'm going to take a slightly different approach than they use in the text, but we're going to let x with the subscript capital T0 of t be a periodic extension of a base function called x of t. And x of t is a limited duration signal. So I'm going to say x of t may look something like this. This is tau, and x of t0 of t is a periodic extension of this function. I'm going to try and redraw it here. And it has, the periodic extension has a period of t0. Of course, these would go on in both directions out to infinity. Since, and so this is what I mean by x of t. It's just the function here that exists between 0 and tau. Because x of t0 is a periodic function, it has a Fourier series expansion, and we can calculate the Fourier series coefficients from in the exponential Fourier series. It's 1 over t0 integral from 0 to t0 of x of t e to the minus j n omega 0 t dt, or since our x of t is of duration tau, the limits on our integral reduce to the region 0 to tau, x of t e to the minus j n omega 0 t dt, where omega 0, our fundamental frequency, is 2 pi over t0. Okay. So the corresponding Fourier transform of x of t, this is just the basis function, so it's not the periodic extension, but the Fourier transform of x of t is, by definition of the Fourier transform integral, it's the integral from minus infinity to infinity of x of t e to the j omega t dt. Again, because our x of t is of finite duration, it only exists between 0 and tau, this integral reduces to this one. And by comparing our formula for Fourier series coefficients to the formula for the Fourier transform, you see that we can get our Fourier series coefficients by evaluating the Fourier transform of the base function at multiples of omega 0. A slightly different interpretation of this result is, again, if we have our x of t, okay, so talking about x of t here, not its periodic extension, and then with a corresponding Fourier transform, it may look something like this. This is x of omega. Then from the Fourier series representation, I know what that results in is a sampled version of x of omega. So I'm going to sketch in x of omega here. actually is the scale factor, so this dotted outline I'm going to draw here is actually 1 over T0 x of omega. Then the dn's are just sampled versions of 1 over T0 x of omega, where I sample this at with n equal to 0 at 0, and then with n equal to 1, I would sample at omega 0, 2 omega 0, 3 omega 0, and then also correspondingly at minus omega 0, minus 2 omega 0, going on out to infinity in both directions. And so we require that in the time domain, since this is of duration tau, and this has a period of t0, and in order for this representation to be accurate, we require t0 to be greater than tau. So there's no overlap of these, this periodic extended version of x of t. So, or equivalently, we require 2 pi over t0 to be less than 2 pi over tau, or we require omega 0, which is our sampling rate in the frequency domain, to be less than 2 pi over tau, which is the duration of our signal in the time domain.